Just like the Kruskal's algorithm, the Prim's algorithm finds the minimum spanning tree of a weighted and undirected graph. And again, like Kruskal, Prim is a greedy algorithm, but unlike Kruskal, it takes a fundamentally different approach to finding the minimum spanning tree. Before we dive down into the actual Prim's algorithm, we need to discuss an extremely crucial fact about undirected weighted graphs. Imagine that you have divided your graph into two mutually exclusive partitions, one on the left and one on the right. Basically, a partition is just a set. So here you see there are a few edges going from the left partition to the right partition. Of these edges, the edge with a minimum weight, let's call it E, as shown here. So the partition principle basically says that the edge E with the minimum weight will be a part of the minimum spanning tree for this graph. Now we are ready to explore the Prim's algorithm. Initially, we randomly choose a vertex, let's say A in this case. Let's divide this graph into two partitions. One on the left side of the blue curvy line is a partition that just contains A. On the other side, the right side of the blue line, is a partition containing everything else except for A. We can color these partitions for a better understanding. There are three edges going from the left partition to the right partition: AB, AD, and AF. According to the partition principle, AD has the smallest weight among these three, so this will be a part of the minimum spanning tree. We mark it. Since D is incident to our newly added minimum edge, we include the vertex D in our left partition. We'll also have to redraw the partition line and recolor the nodes as shown. There are many edges going from the left partition, the blue one, to the right partition, the green one. We pick the minimum weight edge. Here there are two edges, AB and BD, with the minimum weight of 5 each. You can pick any one of these. This will include the vertex B in the left partition. Don't forget to include edge AB in the minimum spanning tree. At this point, we have vertices ABD in the left partition and CEFGH in the right partition. Looking at the edges going from the left partition to the right partition, we find the edge DE has the minimum weight of 13. We include it in the spanning tree. Now, the vertex E becomes part of the left partition. We redraw the partition line and recolor the graph. Note that you can work with the partition line only. Coloring vertices is completely optional and can be skipped. So the next minimum edge is EH with the weight of 2. We select it for the spanning tree. This will include H in the left partition. All of the edges going from one partition to another, that is BC, CD, CE, CH, EG, EF, and DF. The edge EG has the minimum weight of 8. We mark this edge and include vertex G in the blue partition. In the right partition, only vertices C and F are left. Note here that the green partition may look like two separate pieces, but it's actually a single set containing two items, C and F. The minimum weight edge going from the green partition to the blue partition is FG with the weight of 4. So we mark this edge and include F in the blue partition. At this point, all of the vertices are in the blue or the left partition, with only one vertex C that's left in the green partition. The minimum edge crossing the partition boundaries is CE with the weight of 10. So we mark this edge. Also include vertex C into the left partition. At this point, all of the vertices have been included in the left partition and the right partition is completely empty. Our algorithm stops here and we have found our minimum spanning tree. And this was the Prim's algorithm for finding the minimum spanning tree.